So today we are speaker, and I remember when this was presented as an engineering facility, it must have been like 15, 20 years ago, to talk about software activity. So Elaine, who is a retired branch chief who ran this software initiative came out of, will do the introductions of the speakers today, and maybe, and she's one of our active members. So Elaine, would you, let's see, anything else that I need to mention that you guys are aware of?
What was the winning number?
Okay.
3/4.
Right. I'm going to say something for 2 minutes, and I couldn't memorize it because my ability to recall words when I want to is not good anymore. So anyway, Dave and Jonathan, come on up. The three of us retired from Flight Software Branch with 582. And if you remember back in around 1997, Joe Rothenberg was study director, and he decided to reorganize all of the 1,200-person engineering organization away from projects toward division and branches into discipline-focused divisions and branches of similar mission subsystem skills. 582 became the Flight Software Branch, bringing people with flight software skills from 6 engineering branches. So people from the Explorer, Small Explorer, Hubble, out-of-house missions, on-orbit missions, and science instrument developments came together. And we talked about what they wanted out of this new group. And essentially, one of the things they felt strongly about was a truly reusable onboard software system where mission-unique hardware and application requirements of a new mission would not result in changes to the common functionality of a heritage mission flight software. Think of it as defining, developing, validating an OS, operating system, analogous to Microsoft or Mac OS, except our goal was a highly reusable, real-time software system and applications for special purpose flight hardware. And Jonathan Wilmot and Dave McComas are going to do the technical work. Is that what I did?
Yes. And so I'm Jonathan Wilmot. I was in Elaine's branch for many years, and she was quite the enabler for what we came up with. And we've been, and hopefully you'll see, we've been fairly successful with this endeavor. So the software system we came up with is a core flight system. It's got a little c because it's small compared to some other organizations that try to do something similar and had the big C, which can't fly out of little CubeSats and stuff. So you see the range of vehicles that we support. You can run it on your desktop, you can run it on a microboard, you can run it on a drone, you can run it on a balloon, CubeSats. It's on the Orion vehicle as a backup flight software. It will be on the space station, or the lunar space station, as the main flight software. And I'll talk a little bit more about that shortly.
And the space seats.
And space, yeah, it's all over the place. So a little introduction. I'm sorry I have to read it off of here. So the cFS is a software framework, and it's got a suite of applications that are commonly used. And it's created for NASA's mission. It's something NASA created to support our mission set. With science and exploration. It's similar in concept to Android and iOS. It's an open platform, freely distributed, that you can write your application for, so you can share, you can collaborate with different organizations, share software, and some examples of that. You can innovate on it. You can set it up on your desktop in a few minutes and start writing applications pretty quickly and rewrite new software and see it run in really short order. And commercialization. There are a lot of commercial partners, and Dave will talk about the commercial partners that are using this software as well. But one of the major differences between cFS and other software systems, like Windows and iOS, is we're written for Class A, human safety. Where you're following the NPR about what are the processes you need to do that, how do you test it, all the artifacts that you need for certification. And so we're doing that, and have been doing that, and all those things then, because we're open source, other missions and universities get to take advantage of that. They don't have to repeat all that. They're getting Class A quality flight software for free. And it's been quite an enabler. The open source aspect has been a key to this. And we were winner of the 2020 NASA Software Year Award, which is kind of a big deal. So space applications, have some unique challenges. We're supposed to work all the time. Be up 24/7. We're complex autonomous systems. We're robots in space, and we're remotely controlled over millions of miles. Unlike your terrestrial system. So that leads to a lot of challenges. Plus we have to deal with the harsh environments. The hardware we're working on can break. There's radiation effects. The processors are still a couple generations older. We're getting up to a gigahertz now. Desktops have been at 5 with multi-cores for years. And sometimes the speeds can be quite low. If you think about New Horizons out at Pluto, there were 2,000 bits per second. And the system had to work at those kind of data rates for command and control, for the remote part. But that's incredible. It's not gigabits that you're talking about terrestrially. And so one of the key parts of this is that solutions and design patterns and all these things are sort of baked into the architecture. Many lessons learned over the years are part of the architecture itself. So when we reorganized, we got to bring in all these people with different experiences and come up with something that would work generally across organizations. So one of the key aspects is this layered architecture, and we but it's similar to the Android. Users write applications at the top. They don't worry about what piece of hardware you're on, what phone you're on, or any of that stuff. They write applications at the top to do science or do whatever. And they get this framework. And they can have different operating systems for cFS. You can have a bunch of different operating systems, all except for Windows. But anything that's sort of open for real-time, like Linux, VxWorks, or R10s. Because of this platform support layer, you can sit on all kinds of hardware architectures, which is really important. Because the hardware changes. We want the hardware to get better and better and better, but we can still reuse our software architecture. So that's been quite an enabler. So the users, as we'll see, they just write a new application at the top, and they can easily, plug it in and turn it on, and off they go. They can do that in flight, dynamically. One of the other things that have been good about this is that there's a lot of design patterns and things like how do you load up a new table? How do you change this? How do you send these commands? These things are all built in and common. So anybody that's using cFS can use similar ground system with similar command and telemetry interfaces and similar ways of operating the vehicle. It doesn't matter what platform they're on. And one of the important things that happened because of that is the Artemis Accord, which talk about interoperability of systems, being critical to safety, is really important. And so what the cFS architecture and software is actually in NASA's International Deep Space Interoperability Standard. There is a requirement to use cFS across the Artemis program, which is another big one. So we have JAXA, the European Space Agency, the Canadian Space Agency, and any of the international partners are using cFS. And they're getting to take advantage because the mission, Artemis, is a human safety. They're able to take advantage of the Class A certification process, which is very expensive to do that. And you have to repeat it but we have repeatable tests. There's a whole infrastructure that goes along with certifying the CFS for different targets that you get to reuse as well. So I'm not going to talk too much on this kind of chart, but you know, CFS is this engineering complete solution. So it's got all the tests, all the documentation requirements, all the things that actually cost a lot of money. It's not just the code. The code is straightforward to use, but the cost are about the certification efforts and the design documents and all these other artifacts. And they all come with it. So you just have to do your bit of it for your particular target and your mission, but you get to reuse all the common software artifacts to do that certification. That's huge. And that's what, you know, Artemis is taking advantage of that. The Europeans are using the same test environment that the US vendors are using. So it's not just NASA, so it's Maxar and all the vendors and the Lockheed Martins and the Northrop Grumman's that are building this, that are using this. They're getting to do things in a very similar way and saving a lot of money for the program. So let's talk a little bit more about the Artemis program. You know, so if you want to go look it up, it's the International Database Interoperability Standards. The Class A certification is still ongoing because the hardware, you can only certify on your target hardware, and that's not ready yet, so they're not able to complete that certification until you have everything in place. But we're not holding them up. It's the hardware. The Artemis partners are using CFS in their modules, and it's, you know, easily saving tens of millions of dollars across the program, if not hundreds of millions of dollars on all the certification for human safety. A key part of this was being open source. The Europeans and the Japanese and Canadians didn't want to get a proprietary system from NASA. They wanted something that they could use on their other projects as well. And that's actually happening. The Europeans are developing a robotic servicing vehicle similar to ours, and cFS is on that. Again, because of the Class A certification and the high quality of the software. So here's an example of one of the benefits of using CFS across missions. So this was a university that was doing a CubeSat, lunar ice cube, and I think Dave's going to talk about it a little bit. So we had an application we built for PACE, which is a full-up NASA mission developed at Goddard. It's Class B operating system is VxWorks. Lunar ice cube is like subclass D. Its operating system is RTEMS. But one of our engineers, they wanted to use DTN to do a proof of concept for the solar system internet and be the first node around the moon, which went on the Artemis flight, the SOS flight in the fall. And so they wanted to try out this technology. So one of our engineers went down in the morning with the software for DTN, delay tolerant networking. They had it up and running by the afternoon and had integrated and tested for the day. That software was 2 different types of missions, and they had the ground stuff went with it, and they were able to do that in a day, and then they flew that. You can't achieve that without some sort of common framework. You know, the same like Android apps, you can download them to anybody's phone, right, and it's still going to work. Same application, still works on anybody's phone, no matter who made the phone. So we were achieving that. This is a great example of that in the software environment. Another little story about lessons learned for flight software. We have to deal with stuff that breaks on orbit. And so they had a little low-cost CubeSat, some of the hardware broke. And the thing was spinning out of control, but it could get contact for brief periods of time, like a couple minutes. So we broke up the system and using CFTP, we're able to load up little chunks. Tim Ray's one of the CFTP gurus. Load little chunks of the software so that we can, over a period of a couple of orbits, we can get all the software together again, you know, put Humpty Dumpty back together again here, and start up and actually save the mission. It's because we had the built-in ability to load little chunks and put it all together. That's a lesson learned, and it's in our software, and we did that, and we covered the mission, and it went on to succeed. So, another case study, so this is I added this morning, so cFS can save the world. So, the DART mission, which is the one they use to set up and do the asteroid redirect, is running this software. So, you know, at some point you may thank God that cFS was out there so you can save the world. So it was used successfully in the first planetary defense test. It was done by APL, but they're using the software that we freely distributed. So I think that's a good thing. So I just pointed out, the rest of it is kind of quick and just people talking about how great this stuff is. So we had a NASA Software Architecture Review Board do a report on cFS. I think it was back, Elaine was around, it was in 2012 or 13 or something. And this is an important quote because the JPL folks messed this one up. That 582 recognized the truth, and that's not obvious, it bears repeating. It was the software architecture that died, not the hardware. Everybody prior seemed to have failed by making hardware and software common. And here, take this box, and that's our architecture. You know, it's the software that keeps moving and moving and moving and getting developed and improved. And so you shouldn't care what hardware. I want the processors to get faster every year. And I not rewrite all my software, right? So that worked out quite well. And another thing that's part of that review that came out, they responded, they were so surprised that there was nothing we asked about our software that we hadn't already thought about. All these engineers that we brought together had so much experience. It's, oh yeah, we thought about it, that's in there. Oh, we thought of that, that's in there. And they were impressed. It was, we got a glowing report from, you know, this was at the NESC about how good the software architecture was in general. So I was happy about that. Just a quick thing, you know, where are we going next? You know, there's people writing AI programs, they're integrating, you know, the ROS robotic operating system with it. We have partners that have actually changed their hardware a little bit that make it easier to support. We have Simulink, MathWorks has added little features in it to enable better development of cFS software. I think Dave will talk about it. Maybe there's advertisements for employees asking, do you have cFS experience? You know, so industry is sort of picking up on this, which is good. It helps them as well. Universities, and Dave will get to that part, are using all this. I think I guess I won't go on with it. There's a whole bunch of these kind of things in this chart deck, but they're just about the, you know, Johnson Space Center and how much it's really been an enabler for the whole program and how much money it saved, all that kind of good stuff. And you know, there's a lot of, I won't go through them today, but there's a lot of quotes, and they're across organizations. There's, you know, Brazil is using it in one of their CubeSats and their missions. JPL is happy to have this. Yeah, so and this is the, you know, there's a quote from one of the principal investigators about how big an enabler it was for the university to be able to launch a CubeSat in such a short period of time, having this mature software base, and having their students learn how all this gets put together so quickly with all the tools that we have available for it as well. So I think I might conclude there, but it'll take all day's time. I guess other than there's little companies, you know, the Korean Space Agency, which isn't a little company, is using it, as well as a lot of tech startups are using it because it's free and they can build on it. It's like, again, Android. It's not in the low-level software, the infrastructure. It's about all the apps, you know, your AI apps, your automation, your science processing apps. Those are where you should be spending the money. In an architecture like cFS, what allows you to spend money in the right places and don't redo the stupid stuff that has to be there, you know, the basic operating system and the framework. So anyway, we've been able to achieve that, I think. And I will thank Elaine for having the vision to enable the engineers to do the right thing.
That's my idea. So. So I'm Dave McComas, and do a little follow-on. So mine's a little different angle. So Jonathan gave you the background of, the beginning of the cFS, but mine's going to be more. I mean, it's kind of coincidental that the space industry is actually going through a transformation. So I don't know if everybody, how much everybody's been paying attention, but it's really changed in terms of accessibility and commercialization, and we just happen to be at the right place at the right time. And actually, I do want to, before I get into it, I'm going to point out somebody else, precursor to the cFS is Mr. Bruce Vatican, because he wrote the original message bus. Software bus, yes. So, yeah. So we reworked, so I was at 512, and I think you were 740. 735. 735, so that brought, and that's when it came under Elaine's leadership. And I also think the cFS story, it's kind of like the Goddard story in a way, in the science side. So science was always there, looking at the Earth, observing, the cosmos and sharing this with the world. But on the engineering side, we've never really had that luxury. And I feel like going open source, and I'll talk about that a little bit, what that means, and the industry changing kind of gave us this opportunity as engineers to share our stuff. So, real quick, kind of interesting, I put this up here because I started in 1985, so I kind of got indoctrinated to product lines. I mean, the first thing I learned was the multi-mission modular spacecraft system, and this was, to me, was way ahead of its time, because there was this guy named Semolina, one of these guys. So kind of these real leaders, and they came up with a structure that was reusable, where you could put on different instruments. And this was at a time when the computers were, it was the NSSC1, or NIST as we all refer to it, but it didn't have as much memory as this PowerPoint slide. I mean, it's kind of crazy how this framework worked. And then Barbara Scott was my boss on EUVD, so 1992 launch, but that was one of the ones that was, it kind of did really put the seed in my head about you can do this in space with mission systems. But there are challenges, and I don't mean this is a derogatory slide, there's a culture challenge. So when we went open source, so on the left side I have, the Aeronautics Space Act, and there's things, promote technology, contribute to the national technology base, create science and engineering opportunities, and there's a whole list in there. But we go to open source, so what that means is the license of the software, we changed it so people could, with the help of the lawyers, so they could freely use our software. And there's a lot of variations on open source, but the other angle of it, if you're not familiar with software, there's a lot of repositories, so you can put your software up in a repository, and anybody in the world can download it. Well, that's where the question mark comes in. So one of the first meetings, I don't know if you were here, Jonathan, and I think we might have been trying to get money, that was another challenge, was getting project-independent funding for a product line, and Goddard's project-centric. But the first, I was very proud of the chart, because at the time it was something called SourceForge, and it lists all the countries that had downloaded your software. And the first thing that a management person said was, never show that chart again. And I thought, oh, because there were some friendly nations and there were not so friendly nations listed there. And so we were all enthusiastic, but it does take change. And the other big change is, the project independent funding. That's really hard to come by. So one of the things we did was kind of leverage projects with the vision. Elaine had the vision. We did a retreat where we designed a lot of things, but then we had to incrementally add them into the product line as we could get a mission that can sponsor that, in a sense. So that's the open source scene. Now there's a couple charts on where the aerospace industry is going, which maybe a lot of people aren't aware, but this is CubeSat growth, and CubeSats are there's different sizes, but maybe the loaf of bread is a good analogy for the one size. I don't know if you can see the chart, but we went open source in 2015. And you can see that, it just became right at the right time when CubeSat growth was happening. And some of these, and it's also happening across universities, military, civilian, and commercial. So it's just an explosive kind of thing that's happening. So it's 100, 200, but you can especially see in the universities. That's where it's really inspired a lot of students because they can actually build something that gets. And the other thing that NASA's done, and I think Canadian Space Agency, they've had CubeSat launch initiatives. So they have free rides to space. So if they can build the CubeSat, they can get to space, and that's a huge motivator. And the other thing you're starting to see is people are just starting to think out of the box. Now you got these small spacecraft. People watch the InSight, the JPL mission going to Mars, and they have 2 CubeSats flying by the mothership where they can take pictures and make sure everything's healthy, and and they even have some cool pictures of spacecraft with the Earth in the background, so we can do a lot of neat stuff. And the other part of that, it's not just, so now there's the accessibility, but it's also international. So the point of this slide was really just to show, these are all the different countries that are involved with the CubeSats and small sats. This is actually small sats, a little different class. But a lot of us have been contacted by a lot of these people because our software's out there, and they find us and ask questions, which is really powerful. So this slide was more, it's kind of coincidental that these are all around the moon. So I thought it kind of told a story where the cFS is, it just happens to be a lot of things that are revolving around the moon that it's involved in. So this is Goddard's Lunar Reconnaissance Orbiter, and that mission was led by Mike Lau, who, for the flights off of West, not the mission. But that's where we matured the core flight, the first 2 layers. So that was one of the missions where we leveraged, okay, now we have the layers. And a later mission was where we tried to get the apps more mature. So that one, it's still orbiting, doing some great work. So that's got the cFS. And then the talk last month, the Artemis 1 had launched 10 CubeSats. Well, 2 of them are using cFS. So Bio Sentinel is out of Ames Research Center, and I think with the University of Mexico. And then Lunar Ice Cube, which Jonathan mentioned, is using cFS. And that's also got a story behind it because we went out to SmallSat, which is a conference out in Utah each year, and Lunar Ice Cube was having a lot of trouble. And they had a contractor, or it was a university, I think, Bash 8, it's another language, programming language, but their designer, hadn't really got anything done. They just had their preliminary design review. And we were at a SmallSat and showed them on our desktop and said, well, here's a Cosmos open source ground system, talking to cFS right here. You can have it for free. That day, he said, we're switching. So he said, we're going to use cFS for our mission. And then the other thing I had the privilege of being involved in, and this was a really neat, so even if there's a cultural divide, not divide, that was starting to happen with open source, it's kind of interesting, and I have a next slide. NASA headquarters is doing a lot of programs to help commercialization of low Earth and even lunar. So the Astrobotic is in Pittsburgh, and I think my last 2 years, a lot of my salary is paid by this program, where I got to travel up there along with a lot of other Goddard engineers. And our job, we were being paid to transfer knowledge to a commercial company. So it was and it's really exciting to me is because this is supposed to launch in the next quarter this year. And if it succeeds, it's going to be the first commercial non-government lander to land on the moon. So that's kind of and it's got cFS running. So it's really it's been really a neat experience. And so here's a little bit about those programs. In 2014, and this is kudos to whoever came up with this acronym, because this is the NASA thing. Lunar Cargo Transportation and Landing by Soft Touchdown. That's it, but they could call it Catalyst, and the whole point of it was to help commercial and let us do it. And so there was 3 systems, Astrobotic, Moon Express, and Master, and all 3 of them that were selected for using cFS. Moon Express, I think, went out of business, unfortunately, and Astrobotic bought Master. So now it's down to 2. But there's another program called the Commercial Lunar Payload Services. And Astrobotic, I mean, this is decent money going to these companies. So they've gotten 2 of those contracts, and Intuitive Machines, who's also using cFS, has gotten 1 of those contracts. or 2 contracts, but these are in the hundreds of millions, so, but that's kind of what's happening commercial. And I thought this is nothing to do with cFS, but I thought it was funny, because, so you can go to Astrobotic and you can click on their Lunar User's Guide, and you can actually go through and start filling out forms if you want a payload to go to the moon. So it's kind of, it's a whole new world out there where you can, so, and then you can have your CubeSat User's Guide, so they're really commercializing. So anything you want to send on, I think it's $1 million a kilogram, so whatever you want to send to the moon. And kind of to wrap it up, and this is really where I've gotten interested in, the other thing that's happened though with the rapid expansion of the space is, or aerospace community and commercialization, and there is an information education gap. I mean, the one thing I've had feedback for is people coming out of college and trying to write flight software. They're just not, it's hard. And especially in ballistic ground system and simulators. And so I was fortunate enough to go in 2021. My daughter happened to be in Mexico, and a team I met online was using the cFS for their CubeSat. So I went down, I managed to go down and be able to do an in-person workshop with this group. And what was kind of impressed upon me, I'm in the middle of the workshop and they stop it, and the president is, the university has multiple campuses, so the campus president comes in the classroom and he says, I just want to thank you because you're building, this is a national thing for us. Because our government hasn't put up a spacecraft. They bought them, their whole Mexican telecom, they bought from the Hughes and the big American companies. He goes, but you're building the infrastructure for our students to become who we need to do the thing we want them to do. And it just kind of hit me because I was like, I'm just helping a fellow engineer. I'm not going to line, I'm going to go help them code. But to them, it was a whole different frame of mind. And that's what's happening in some of those other pictures with the scope of this whole commercialization. So actually, I started, that kind of inspired me. I have a nonprofit called Open STEMware, and it's all based on cFS projects. And I have a couple, I think that's Jan for it. This one I did not do. I did not create this, but this is something Alan Cudmore, who couldn't make it, but this has been a teaching tool. It's a Raspberry Pi, which is like a hobbyist processor board. He 3D printed the whole structure, but this runs the cFS. It's got gyros on it. It's got temperature sensors, and the kids love it. I mean, because you can connect this to a ground system and show them it moving and things like that. And the other thing is, this is going to take 2 hands, but this one, this is a prototype. And this is actually something that I'm working on for a University of Maryland class, and it's based on something called TableSat. So it uses fans as actuators, and Lissy Vess is an engineer at 590, and she did this for her thesis. And it's got light sensors, it's using this Raspberry Pi and the cFS running, and it's just literally, it's got one of those, what do they call it, fidget things that spin really nicely. But anyway, this is the kind of stuff that really engages the kids, and it's all free software. So that kind of wraps it up. I don't have anything more. I don't know if there's questions.
Yeah, how do you manage changes to the cFS?
That's a good question. And Jonathan might be better poised because he's worked with, but actually it's a NASA-wide configuration control board that Goddard is the chair of. And so anybody can write issues. And one of the changes with the most recent open source licensing, we can actually accept contributions as well. Because that's the other challenge is even if people write issues and you don't have the funding, you gotta, I don't know if you have anything to add to that.
That's right. It's very much configuration control. No code gets in there without proper process.
Yeah.
It's not like it's, here, I have some stuff, go easy. No.
So it's always upward compatible and backward compatible.
That's a challenge. Between the app layer, right, exactly. That's actually a challenge.
Thank you.
Tim, sorry, Tim?
I think I have 2 questions. Do you only have sort of one flavor? Like, there might be different communities that have different needs for what their cFS would provide, maybe different speeds, high speed. do you have multiple versions, or is the CFS just one product that?
We talked about that a lot, like a CFS, I guess that's a really small C. But I don't know, about different CFS light or something. But you probably better the answers, because I know in general it's too many parameters. But
We didn't have the resources to really explore other things, so we just picked the minimum performance set. You know, it takes a 32-bit processor, you have to have 3 beta RAM. So there's no, we never did what we call the micro CFS.
The reason I brought it up, I mean, it's so hard to maintain one piece of software, and then if you have like this, the vanilla version, and then you have the high-speed version, and then you have the super small version, it can be overwhelming to try to test and validate all those different versions. So how many versions do you offer? I still don't know, is it 2 or is it 1?
it's one. It's one, but it has tunable parameters that can help.
Yeah, that's fine.
Do the scaling.
That's the way to go, right?
You know, I think an important aspect of that, and this again, because of collaboration. Johnson Space Center developed a automated test suite that takes the parameters, the tuning parameters, and brings them into the test so that you change the tuning parameters in one place, and all the tests auto-run against that set. And they needed it, and everybody actually needed it, but they needed it because of Class A certification. It has to be tested exactly the way you're going to use it, on the hardware you're going to use it, and they want to be able to tweak stuff and instantly rerun all the testing. And that's all automated.
Awesome.
Yeah, that's
Or do you guys stand on it?
I think it's very impressive and wonderful what you're doing. When I worked at Goddard, the International Traffic and Arms Regulations, ITAR, were overwhelmingly dominating all technology. And even before I retired, that started opening up a little bit. But if it's totally open source, what's to prevent the bad guys from getting your software and using it to, you know, attack Ukraine or something like that?
Right. No, we'll share the same thing, I'm sure. Well, I mean, it went to the lawyers and went through the whole ITAR review process, and we did not open source apps that have interface boundaries. So we're more the plumbing, but if the command ingest, we call it, or telemetry output, and any of those apps are proprietary still.
There's like,
But it's open source, anybody can get it.
No, not the.
well, think of it like Linux is open source, and anybody can use Linux anywhere, but it doesn't mean you have a drone flying anywhere, right? It's the attitude control stuff, the AI, the automation, those are not open source.
Yeah, they're not open source. So we didn't open source the secret sauce. We open source all the plumbing.
We didn't even try to get that to ITAR because you know that's typically customers. Oh, I'm sorry. Yeah, we actually were really careful about that. So again, it's like we just open source the framework. It's like Linux. It's like or Android, right? But not all the apps.
Not all right. And that's what, so like a university doing a CubeSat, right? It gets them up and running fast, but the particular app for their mission is something they develop.
American universities.
No, I understand.
But, you know, how about North Korean?
Right.
And North Korea downloaded it, Iran downloaded it.
And I was told that. But we didn't give them anything that they can control rocket with. They can't. We gave them things that help with memory management and things like that, but not any of the critical.
So I wanted to add the other thing. So our 3-letter agencies have actually done quite a few analysis of CFS. They might have found some stuff that they're keeping secret, but they've gone through that to make sure we're not exposing anything we shouldn't. And so we've got their acceptance, and actually they're helping make it more secure.
And I guess one other point, even that command ingest and telemetry output, they're based on international standards that are open. So they're not, we didn't open source those apps, but even the apps we have are just implementing a spec that's anybody can download. So were there any other questions? No. All right. Thanks. Sure. Thank you.
Thank you, Jonathan and Dave and Elaine, for not interfering as Is there anybody here that this is their first meeting, not necessarily just retired? Okay. Are these going to be repeats, or is this because of the speech? Because you do have a lot of
Yeah, I'm Brian Ream. I work for LA2 in Barber Scott and work with Ron and a bunch of friendly faces here. I retired from NASA in 2019, went to work for a contractor, Carroll Douglas, SSAI. Worked there for 3 years and I retired at the end of January last year. I worked on 2 projects in my time at Goddard, Hubble, and James Webb. And my role at James Webb was the Observatory Test and Integration Manager for all its systems, from Goddard to Johnson to Los Angeles, launch site. And once we launched on Christmas Day of 2021, came back, got COVID, didn't go back and clean up and said, I think I'm done.
Hi, my name is Kevin Grady. I retired in 2018, late 2018. Worked at Goddard for a little over 40 years as a civil servant. The last 25 years I was a project manager. I managed 2 flagship missions and some smaller ones as well. Still live in the area. Can't convince my wife to go farther south where it's warmer in the winter. But let's see, over the years I worked Solar Max, Landsat 4 and 5, EOS Space Station, Ron here, Space Station Work Vantage 3, EOS Terra, NPP for a while, the Fermi, we called it Glass at the time, and then finished on what was called W first, but it's now the Grace, the Roman Space Telescope. That's about it.
Recent retirees are a good source of future presentations.
Hello, everybody. My name is Tim Ray. I worked in ground software. I was really lucky when I started. I had a 40-year career at NASA. When I started writing software, they asked me to write the software that command the satellite and send the commands to the different antennas around the world. And then there was another mission that followed that, and they asked me to write the software on that one for commanding as well. And I said, that's fine, yeah, sure. And then there was a third mission that came after that, and they asked me, would you write the software for commanding on that? And I think a lot of engineers and programmers would have said, yeah, I've done that, let me do something different. But I've always loved to canoe and hike and be outdoors. And so I thought, well, sure, yeah, because people know I can get the job done, and I'll be able to go out every day that's pretty. I'll be out canoeing and enjoying. They don't have to go to too many meetings. And then there was a 4th mission and a 5th mission and a 6th mission. And then they started this CCSDS International Standards Group, and they needed someone from NASA who was an expert on spacecraft commanding. And my name came up, not because I'm all that smart, but because I've been doing it over and over. I was an expert. And so then I got involved with designing these protocols that were mentioned that are what the commanding and telemetry are based on, and the CFDP, which is used to transfer files back and forth between space and the ground. So, and now I'm retired. And I'm here because of Bruce, and because although I'm a ground software person, I always loved Elaine Shell and her whole group, and they had the best Christmas party, and I always enjoyed going to their Christmas party and became friends with a lot of them.
Thank you, and thank everybody, and I hope these newcomers come back, and the regulars are here to greet them, and we'll see you next month, I guess. And that's it. Thanks.